We are going to talk about the some elementary transformations on the independent variable of signals. Now, these transformations they play a very central key role in classifying signals and systems, characterizing their behavior, their properties, and the way they handle the signals. So for example, you see if you have a system, okay, let's say it's a continuous time system which is going to handle continuous time signals, okay, and let's say for a certain continuous time system, we are going to have an arbitrary input x of t, and the system does some manipulations, okay, on the signal to produce an output that is yt, or okay, after certain operations on xt, the system produces an output yt. Now this system could be anything, okay. I mean, it could be a filter, for example, which can remove some undesirable noise, okay, from certain bands of frequencies which is not desirable, to produce an output which is, for example, a filtered version of xt, okay, or in some sense it's an enhanced version of xt, which does not contain some undesirable signals which have contaminated xt. So, okay, let's say yt is a filtered version of xt. Okay, now to classify the system, if it is, for example, let's say if it is time invariant, okay, what we do is we introduce another input to the system. Let's say this input is xt minus t naught, and what it means is that the system is simply is going to handle the same input. I mean, the input is the same, the waveform is preserved in xt minus t naught. It is simply shifted in time. The time axis is not completely modified. The modification is just that, for example, if xt was something like this, okay, or if xt is your piece of music or a recorded data on the time axis, okay, and these are the amplitudes, and this is xt, then whatever is the reference, let's say this is your reference where it starts, then t minus t naught will be, for if t naught is a positive quantity, it simply shifts. It simply shifts itself. Okay. So instead of starting from the time reference over here, it's going to start from here. Okay, and then the amplitude stays the same, right? So this is your x of t minus t naught. Okay, so that's t minus t naught. Now, if the output to this wave preserving transformation is the same as yt, instead of yt it becomes yt minus t naught, we say the system is time invariant. That is, it does not introduces any time variance whatever operations the system does on the signal. The output yt is delayed by the same amount as the input was delayed. We say the system is time invariant. Okay, the system is time invariant, or TI. So you see these transformations, which, for example, we do on the independent variable, which is time in this case, are very important to classify and to describe the properties of the system. Okay, so for example, over here, if the output is not delayed by the same amount of the time by which the input was delayed, t naught, then we say the system is time varying. Okay, so we don't know if in case of if it is time varying, then it is some t comma t naught, and we don't know how much delay. Let's say this is t1. Okay, if it is delayed by some other amount, t comma t1, then it is time varying system. Okay, because the amount of delay that the output suffers is not the same as the amount of delay that has been introduced in the input, then we have a time varying system. So these transformations on the independent variable, they play again a very important role in characterizing the behavior of the system. So you see these elementary transformations will allow us to characterize and reduce some several basic properties of signals and systems. So you see in this section we'll focus on very limited but important class of elementary signal transformation that involves simple modification of the independent variable, and in our case the variable of interest in most of the cases will be time axis. Okay, so like for example, you have a, for example, if you have a high fidelity audio system, okay, it could be a piece of music, it could be a piece of speech, whatever it is, it's stored in a compact audio CD, or it is on a magnetic tape. And this recorded data, for example, if you want to play this data at twice the speed, okay, then the modification on the time axis will be, for example, instead of t, it will be x2t. Okay, so for example, if you have the recording xt or a music signal, okay, this is a piece of recorded data like this, whatever it is, any arbitrary, say, consider any arbitrary waveform, okay, which is representing an piece of recorded data. If you want to play this data at twice the speed, well, what you have to do is you have to transform this axis t to 2t. Okay, so for example, x2t will be a compressed version, of xt. Why? Because you see, at, for example, at t equal to 0, okay, whatever is the amplitude at t equal to 0 is going to come over here, and then it has to compress itself in time, so that it plays twice at its speed. So if this amplitude is at it occurs at 1, okay, then x2t means at t equal to 1, so this is 1, okay, this is 1, or this is 1, same time axis, 2, 3. So you see, at 1, then this is half. Okay, this is half. So whatever is true at x equal to 1 in this upper figure is true at x equal to 2 into 1 half at t equal to 1 by 2, right? This is going to make x equal to 1. This is going to make t equal to 1. Okay, so for example, this amplitude is going to start a little bit earlier, okay, and this compression happens at the rate of at 2, okay, at twice the rate. So this crest occurs before 1, okay, and that occurs at 1 by 2. Okay, so this has to occur at twice the speed. Similarly, this, for example, if this this trough, this minima is occurring at local minima is occurring at t equal to 2, then this has to occur at t equal to 1 in x2t, right? Because you understand, I mean, you see the data, for example, whatever is true at x equal to 1 has to be true at t equal to 1 by 2 in this figure, in this figure down here. And similarly, this whatever is true at x equal to 2 will be true at t equal to 1. So this will be 2, this will be 2 into 1 is going to produce the same amplitude as x2. Okay, so this is the compressed data. Similarly, and the physical interpretation of x2t is that you are playing your audio tape or the recorded media at twice the speed. Okay, or vice versa. If you have to consider the signal x t by 2, then you are simply stretching the signal. You are going to downplay the speed of the recorded data. So the recorded data is being played at half the speed in the case of xt by 2, for example. Okay, so these are the elementary transformations. Okay, the transformations could be a time shift. Okay, this time shift could be on the right or could be on the left, depending on if t naught is a positive quantity or could be a negative quantity. Okay, similarly, you can stretch the signal, you can compress the signal, depending on if the quantity is a fraction that is being multiplied by the independent variable, okay, or it is an integer. So these transformations, we are going to use these transformations in our analysis of signal systems later on to characterize the behavior of systems. So you see, for example, in a high fidelity audio system, an input signal representing music is recorded on cassette or compact disc is modified in order to enhance the desirable characteristics, to remove the recording noise, or to balance the several components of the signals, for example, treble and bass. So all these transformations, they tend to somehow improve the desirable characteristics of signals as required. So let's go on and consider analytically these elementary transformations. So a very simple and important example of transforming the independent variable of signal is time shift. Okay, we have talked about this before. Now this time shift is also applicable. It's not only for the discrete time signals, continuous time signals. We can also do the same operations on discrete time sequences or signals. So x of n, what is a discrete time sequence? Okay, and if n naught is considered to be a positive quantity, n naught is a positive quantity, you see all the signal, all the samples over here are simply shifted to the right by the amount n naught. Every sample is going to be shifted by the amount n naught towards right, given n naught is a positive quantity. Okay, it's not like, for example, this sample, whatever the sample is going to occur at n naught. It's going to suffer a sample. It's going to suffer a delay. It's going to experience a delay of n naught. Then this sample naturally will occur at n naught plus 1. Okay, n naught plus 1. And this would occur at n naught plus 2. And this is exactly what is happening. So this sample is at n naught plus 1. Then the next sample is at n naught plus 2. Okay, and this trend continues. Similarly, this sample, the previous sample, this was n naught. The previous sample before n naught is going to be n naught minus 1. So you see, each sample is experiencing the same delay n naught. It's not like, for example, this sample is going to occur before. The waveform is going to be preserved. So time shift is a waveform preserving transformation. Okay, the time shift in a discrete time sequence or a signal is illustrated in the figure below, which we have seen over here, in which we have two signals, xn and xn minus n naught, that are identical in shape but are displaced or shifted relative to each other. So they're just shifted. The shift is towards right. Okay, n naught is a positive quantity. On the other case, if n naught was to be a negative quantity, if it was to be a negative integer, then it would have been advanced or shifted towards left. Okay, so the time shift is a waveform preserving transformation. The shape of the waveform, for example, the shape of the waveform has stayed preserved under this transformation. There is no delay that becomes a function of the position of the sample. Okay, it's independent of the position of the sample. All the samples are being shifted by the same amount of the delay. So it's a waveform preserving the waveform. The shape of the waveform is preserved, but the shift could be either towards right, it could be towards left, depending on the amount of n naught over here. Okay, which is in the discussion. It could be positive or negative integer. Okay, so we'll also encounter the time shifts in continuous time, in which your independent variable is t, so that represents a delay. If t naught is positive, it would be advanced towards left. If t naught is negative, these are the delayed version of xt. So this figure shows the discrete time signals related by time shift. In this figure, n naught is positive quantity. Okay, and so xn minus n naught is delayed version of xn. So each point in xn occurs later in xn minus n naught by amount n naught. Okay. This figure is the depiction of two signals which are related by a time shift, and over here t naught is a negative quantity, and you can see the shift is towards left. Okay, if t naught is a negative quantity, then you have to advance the signal. Okay, you have to shift this towards left, so that xt minus t naught is an advanced version of xt. It means each point in xt corresponds to the earlier time in t minus t naught. Physically, where it happens is that these signals, for example, they are related in this fashion, arise in applications such as radar, sonar, and seismic signal processing, in which several receivers at different locations, they observe a signal which is being transmitted through a medium, water, rock, and air. Now these mediums, they have different, they introduce different propagation delays, and owing to different propagation delays, although the waveform stays, the shape of the waveform, the overall waveform, the frequency content, or the information, it stays intact. However, the signals can be, owing to different propagation time, the signals could suffer different delays or could be time shifted. Okay, so in this case, difference in the propagation time from the point of origin of the transmission of the signal to the receiver, to any two receivers, result in a time shift between signals at two receivers. Okay, and this propagation delay or waveform shift doesn't means that the information is lost. It's simply the shift of the waveform. Okay, so this is a physical interpretation. This is what happens in receivers which are located at different locations. Okay, so second basic transformation of the time axis is that of the time reversal. Now, for example, illustrated in the figure below, x minus n is obtained from the signal xn by reflection about n equal to 0. So you see, whatever is true, for example, let's consider these two signals. These are two discrete time sequences. Now, whatever is true at, so let's say this is 1. So this sample is 1. So this sample is x1. whatever is true at n equal to 1 will be true in xn minus 1 at n equal to minus 1. So this sample is going to be flipped about the vertical axis like this. Okay, so this occurs at x equal to minus 1. So this will be, for example, minus 1, and this is going to produce under this transformation, this will be x1. So for all the samples, see this sample, and for x2 it will be at x minus 2. It's just like flipping your original sequence around the vertical axis. Okay, so the sequence is flipped around the vertical to the samples on the left of n equal to 0, which are occurring for the negative indices of small n, they're going to be flipped, okay, around the vertical axis. So this axis acts as a mirror for the samples. Okay, this axis n equal to 0 is going to be the mirror, and under this transformation, whatever is the amplitude or the data that you have at n equal to 0, it stays intact. So n equal to 0 stays the same. Okay, the sample at n equal to 0 stays where it is, and it has the same amplitude in both cases. But however, the samples on either side are simply flipped over. It's, or you can say they're simply the mirror reflections around n equal to 0. Okay, and the same goes for the continuous time case as well. Simply again, it's the t equal to 0 is the mirror around which you're going to flip your signal. Okay, physical interpretation of this is, for example, if you have an audio tape and you want to play it in reverse manner, so that the playback is reversed. So this is what you're going to experience. Okay, so similarly as depicted, the signal x minus t is obtained from the signal xt by reflection about t equal to 0. So that is, if xt represents an audio tape recording, then x minus t is the same tape recording played backwards. Okay, so this is the physical interpretation of time reversal. A third transformation is that of time scaling, okay, of practical interest. So what happens is that, and you see in the figure below, we have illustrated three signals, xt, 2t, and t by 2. So what happens is either you compress the signal if you're going to multiply t by an integer that is greater than 1. Okay, so you see, for example, if this is 2, okay, and this is minus 2 on the time axis, this is 2 seconds, minus 2 seconds, then this will be 1 second, this will be minus 1 second. Okay, and the interpretation is the same mathematically. I mean, analytically, if you look this closely, then for this figure, this at t equal to 1, this becomes x2 into 1. This is x2. Then originally at x2, the amplitude of the signal goes to 0, right? So amplitude of the signal goes to 0. This could be either plus 1 or minus 1. So plus minus doesn't matter. On both sides, plus minus 2, plus minus 2, it has to go to 0. And so this results in compression. Okay, although under this transformation, whatever is true at t equal to 0 stays intact. So t equal to 0, the information of the amplitude at t equal to 0 stays intact. However, on both the left hand side and the right hand side of the signal, the signal is simply compressed. The signal is compressed by a factor of 2. And this, if this is a piece of the audio, then that means you're playing the audio at twice the speed. Okay, because the amplitude, for example, at t equal to 0.5, you require the data that is present on the original signal at t equal to 1. Okay, so whatever is present at t equal to 1, has to be played at t equal to 0.5. That means you're playing the signal at twice the speed, right? You're playing the signal, you're playing the music or a piece of speech at twice the speed. So x2t is simply a time compression. X2t is simply a time compression, as can be seen from here. So, I mean, at every point in time, whatever is the value of the signal xt has to be played at twice the speed if the transformation is x2t. Similarly, if the transformation is xt by 2, then if you can guess this right, this will be t equal to 4. Okay, and this will be equal to t equal to minus 4. That simply means every point in time on the signal is stretched by a factor of 2. So every point in time has been stretched by a factor of 2. So whatever is true at t equal to 1 is going to be true at t equal to 2, right? So this at 2, the signal does not goes to 0. Instead, it is simply stretched at by a factor of 2. Therefore, um, this is a slow playback, which is, I mean, by a factor of twice, you are playing your piece of recorded data at a slower speed, at half the speed. Okay, so these all transformations are related by linear scale changes in the independent variable. Okay, so I mean, you can work this out. This is very easy. So if you have to calculate for the samples, then at plus minus 4 by 2, 4 by 2, this is equal to x of plus minus 2. And if you're going to refer this, if you're going to relate this third graph with x, the original xt, so the original xt at plus minus 2 is 0. So therefore, at plus minus 4, xt by 2 has to be 0. Okay, so this is the transformation. The linear scale is just stretched or compressed. So this figure is showing the continuous time signal related by time scaling. So if we again think of the example of xt as a tape recording, then x2t is that of the recording played at twice the speed. Xt by 2 is a recording played at half the speed. Okay, so this is the physical interpretation of scaling the time axis, right? Okay, now if you consider arbitrary analytical transformation of the signal, which are often of interest to determine the effect of transforming the independent variable. So let's say for a given signal, you have to obtain a signal transformation of x alpha t plus beta. I mean, this becomes a combination of what we've talked before. For example, this alpha is going to give you the amount of compression the signal is going to undergo, and this beta is going to give you the amount of time shift. So it's the combination of both time shift and the compression. For example, where alpha and beta, if they are numbers, then such a transformation of independent variable preserves the shape of xt, except that the resulting signal may be linearly stretched if alpha is less than 1. It could be linearly compressed if alpha is greater than 1. Okay, and it could be time reversed if alpha is negative. It could be time shifted if beta is non-zero. Okay, beta is non-zero. Of course, the shift could be either to the positive time towards the positive time axis towards right, or it could be towards left. Okay, depending on beta positive or negative. Beta is positive or negative. Similarly, if alpha, for example, if alpha is less than 0, if alpha is equal to minus 1 and beta is 0, then this simply means time reversal. Okay, so if we have this transformation f x alpha t plus beta, then in the case where alpha is equal to minus 1 and beta is 0, but what does this imply? This implies simply the time reversal, right? This is simply the time reversal. The signal is simply flipped around the vertical axis. So or if you have a piece of the recorded data, it is simply being played in a reverse manner. Okay. Similarly, if your alpha is say alpha is over here, beta can still be 0, but alpha is a positive quantity. Okay, alpha is a positive quantity, and beta is 0. So okay, beta is 0 and alpha, the magnitude of alpha is greater than 1, then it simply means you are compressing the signal, right? So if alpha is greater than 1, then the time scale is linearly compressed. So this results in x of alpha t. For alpha greater than or equal to 0, this implies time compression. This implies time compression, Tc. Okay. This implies time reversal, Tr. Similarly, if you have the same transformation, and now we are considering the general transformation alpha t, we're combining the compression and with the time shifting. Again, if beta is 0 under such a transformation and the magnitude of alpha is less than 1, it could be 0.5, it could be 0.3 or whatever, then this implies again that x of alpha t results in time stretching, ts. Okay, this is time stretching. So if beta, again with alpha, if alpha is anything and alpha is any positive quantity and alpha is not equal to 0, if beta is positive or negative, then the time shift could be advanced or it could be simply a delay towards right. So alpha, if alpha is not equal to 0, okay, it could be anything, and beta is greater than 0, this implies time shift. This implies time shift. This implies time shift. Time shift could be either towards right, it could be towards left. In case if beta is greater than 0, the time shift is towards right. In case if beta is less than 0, if beta is less than 0, then time shift is towards left. Okay, so for non-zero beta, it is simply a time shift. Okay, together with compression or stretching, depending on if alpha is magnitude of alpha is greater than 1 or less than 1. So let's consider this example. We have certain transformations shown here with regard to the signal xt. It's an arbitrary signal. If you consider xt plus 1, you see alpha is 1, so there is no, in this case, in the first case, alpha is 1, so there's no stretching or there's no compression, right? You don't need to worry about stretching or compression in this case. And same goes for the part C over here. Over here as well, you see alpha. Well, alpha is not equal to 1, alpha is equal to minus 1, right? And we can see that with regards to xt, it is simply flipped. It is flipped around the vertical axis, but it is also delayed because beta is non-zero. Okay. Let's discuss the first case. So alpha equal to 1, and beta in this case is also 1. Now let's try to understand how we can construct this. I mean, we know that, okay, since beta is can we say this, according to this transformation alpha t plus, okay, beta is 1, fine. The signal is simply advanced. Why? Because at t equal to 0, this will be x of 1. Okay, this will be x of 1 at t equal to 0. Then at t equal to minus 1, this function becomes x of 0. Then at t equal to plus 1, this function will take an amplitude value in the original signal corresponding to, well, this will be 2, right? At t equal to 1, I'm just substituting the values of the time axis at 3 different instants. Okay, so t equal to 1 corresponds to 1 plus 1 is 2. Now in original signal, xt is the original signal, right? So what is x2? x2 is 0. And this 0 is occurring at t equal to 1, right? Similarly, at t equal to 1, well, the original signal is 1, right? But at 0, this is x equal to 1, right? So at t equal to 0, 0 plus 1 is 1, so this is x1. So x1 corresponds to what? This is 1, the amplitude is 1, right? So this is x1, this is my x1, this is my x1. Similarly, this is my x0, where the transition is occurring from 0 to 1, right? I have a jump transition. So where does this x0 occurs? Is at t equal to minus 1. So if t equal to minus 1, then my argument becomes 0, right? So at 0 in the original signal, there is a jump from 0 to 1, right? So this jump discontinuity, this jump discontinuity simply shifts because of the transformation t plus 1 at t equal to minus 1. Okay, to make this 0, I have to consider the time instant at t equal to minus 1. So the argument becomes 0, and I have the data that is true, and the signal xt at t equal to 0 occurs at t equal to minus 1 in xt plus 1. Okay, so this implies since alpha is 1, there is no compression or stretching, but owing to the non-zero beta, I have an advancement, right? I have a time shift. Basically, I have a time shift. Okay, now this time shift could be either left, reverse, right. In this case, the time shift has occurred towards left. Okay, so this is how you can go to the basics and relate whatever is the signal. I mean, all the signals that are shown below are of the form x alpha t plus beta, right? So how you compare this with, I mean, if you have to construct the waveform for this transformation, whatever alpha and beta are, you just have to relate this with the original signal at some particular time instance, and that is going to give you the shape of the waveform. For example, we have considered at 3 time instants, okay, the shape of the waveform. We don't need to go beyond, because, for example, xt is 0 beyond t equal to 2, it's 0 below t equal to 0, and this 0, for example, has been transformed to t equal to minus 1. Then this 1 has been transformed to t equal to 0, 2 has been transformed to t equal to 1, and thereafter, since the 2 has been transformed to t equal to 1, thereafter the signal is 0. We don't need to consider more points. Okay, so 3-4 points are enough to construct any arbitrary general transformation if you know beta corresponds to the time shift and alpha corresponds to the stretching or compression of the signal. Let's consider this signal. What is going on over here? We are experiencing a time reversal and a time shift as well. Both the cases are true in part C. So what happens at, for example, at 1 we are going to have at t equal to 1, okay, t equal to 1, we're going to have x of 0, right? Similarly, at t equal to 0, we're going to have the amplitude x of 1, right? Similarly, at t equal to minus 1, we're going to have x2, right? So let's see if we can relate these amplitudes with the original signal and see, just verify if this waveform is correct indeed as compared to the amplitude in the original. The original signal is, again, whatever is, the amplitude at xt occurs at t equal to 0, t equal to 1, and x equal to 2. That's what we are going to relate to construct x alpha t plus beta. For example, x0, we know that it has a jump discontinuity from 0 to 1, and this jump discontinuity and minus t plus 1 occurs at t equal to 1, right? Because t equal to 1 is required to make the argument equal to 0. So this is okay. Then the next point is t equal to 0, where the signal, the argument that the signal takes is 1. Okay, so at x equal to 1, at t equal to 1, in the original signal, the amplitude is 1. So this is correct as well. Then this 2 is occurring at t equal to minus 1 under this transformation, because at t equal to minus 1, minus 1 is 1, 1 plus 1 is 2. So x2 is having 0 amplitude over here. So this transformation is correct indeed, and this depiction, this graphic of the signal under this transformation is correct, right? So x minus t plus 1 correspond to the flipping of the sequence, and flipping of the sequence around the vertical axis, and then time shift of the signal by 1 unit towards right. Okay, so it's 1 unit towards right. So first either you can flip the signal towards on the vertical axis, and then you can shift it towards right to have this graphic. Okay, so always the case is that you can always revert back. You can always put some values of t, and you can relate those amplitudes with the original signal. Whatever are the amplitude of the original signal will have to be true under that transformation. Okay, so that's how you can construct the graphic under any elementary transformation. Now, for example, this is a simple case where beta is 0. Right? The beta is 0. Alpha is greater than 1, which means time compression. So alpha, you see the magnitude of alpha is greater than 1. So this simply refers to the time compression. And this time compression occurs at the rate of 1.5. So this is 3.5. So that means at 2 by 3, if you substitute t at 2 by 3, then this becomes x of 1. And we know the value of x of 1 is what? X of 1 is 1, right? This is 1. And we know what is x2? x2 is 0. And where does this x2 occurs? Is at 4 by 3. So this 4 by 3 into 3 by 2 is 2. Okay, so this is x2. This is 0. And under this transformation, again, at t equal to 0, this jump discontinuity stays preserved. Okay, so there is no time shift. This is simply the time compression, of the original signal by a factor of 1.5. It's simply compressed by 1.5 times. Okay, then for example, if you have over here, you see beta is 1 and alpha is still the same, that is magnitude of alpha greater than 1, so we can expect time compression, but we are going to expect a shift in time as well. Okay, and you can see what you can do is you can simply compress this signal, and then you can shift the entire sequence, this signal, by 1 unit towards left. Okay, so this signal has been shifted by 1 unit towards left. This to make this simpler, again, if you can go back to the basics, that is, You substitute the value of 2 by 3 over here. This is going to produce 1. So this is your x2, which is 0. This is x2. Then at 0, this is x1. This is x1. x1 is 1, x2 is 0. We know that in the original signal that is the case. Similarly, minus 2 by 3 is going to produce x of 0, and x0 has the jump discontinuity which occurs at minus t by minus 2 by 3 under this transformation. So this under this transformation, 3 by 2t plus 1, this is how the signal looks like if you compare this with the original signal. Okay, so for each transformation, for any arbitrary transformation, whatever the alpha is, whatever beta is, don't worry how dominating it might look, but you can always relate the amplitude of x alpha t. You can make some substitutions for t. You can relate this with xt, and you will have a graph. You don't need to confuse even yourself with if you have to time shift first and you have to, or you have to time reverse first, and or second you have to shift in time, or you have to do the shift in time first, or you have to time shift first, or you have to do the compression later on. Well, don't get yourself confused in there. Many literatures do that. The best way is to again just relate the values of the amplitude under this transformation with the original signal xt, and you're good to go. I mean, you will have an idea how the waveform will look like. Okay, but as a general rule, few things to keep in note is that alpha always refers to time compression or stretching depending on the magnitude of alpha. If it's greater than 1, that's time compression. Less than 1, it is time stretching. And again, for beta, if it is non-zero, it requires time shift. Okay, so that's all.